Okay, good afternoon. So let's get started. Need to do one quick correction here for my touchpad thing. Then I'll be ready to go. All right. So, welcome. We've got my aquarium here. Little fish inside. Maybe he'll come to the front for you. And today we're just going to have our virtual makeup class to keep going with our course. Today we're going to talk about chemical equilibrium reactions and essentially what were they used for, where we see them, and what types of problems can we solve, what kinds of applications are relevant for equilibrium chemistry. So last time we left off here where we talked about kind of how the equilibrium is reached and the fact that it is a matter of equal rates going back and forth, not equal amounts being on one side or the other. So we watched that little video. We talked a little bit about the pH system. We will expand on that a bit today, and then we'll have some example problems. If you have any questions, I think you need to sign into Twitch, meaning you might have to register for an account. I've heard that some people have had a problem with that. I'm not sure what I can do for you. Perhaps I can try on the Twitch website to see if I can allow comments from non-users, but then we have a risk of getting spammed out by robots. So do me a favor and create a Twitch account if you are interested in commenting or asking questions. I would appreciate it just knowing that those of you who are here and watching are actually participating, tracking well. It looks to me like the sound should be good, but it's always a good thing to have one of you confirm that everything's operating as it should be. Okay, so with that, we'll get back into it. And thank you. So we'll get back into it here with where we left off. So we talked about these equilibrium reactions, meaning that they are essentially a pair of reactions, one going forward and one going backwards. So water, for example, can dissociate into H plus and OH minus. However, that reaction can go in reverse where we have H plus reacting with OH minus heading over to water as a product. A lot of times the way we will describe these or write these out will be the molecule that is doing the dissociating would be our reactant, and then the dissociation products are the products. In a way that's arbitrary, but that is the standard way of it. So if you see something that's losing a proton, something like that, then that should be, that's the dissociation, and that should be on the left side. There is a good distinction to be made here. I think we mentioned last time that there are like combustion, that's a forward reaction. There's no way to uncombust something. There are some other reactions that we really don't expect to be going in both directions. So let's say sodium chloride dissolving to form Na plus and Cl minus. Technically we could have a backwards reaction, but it's so soluble that we're almost never dealing with the type of system where we're actually going to have sodium chloride solid being formed. We have to have a super saturated system, and that just requires a whole lot of salt. So technically that is an example of a solubility product, but that's one that usually we can treat as just a forward reaction. So sometimes we'll deal with problems that say, if you ever see completely dissociates, then you can just assume that was just a forward reaction and you're not worried about the equilibrium. So if you see that on a problem with something like sodium chloride, that means you can ignore. Let me be careful here. Yeah, that should generally mean you can ignore a reverse reaction. And we'll take a look at some problems and how they're phrased to be sure that we can really have a good handle on that. Okay, so we described the math in terms of what the equilibrium constant looks like. We introduced the fact that we have water in equilibrium like that. And so I want to just recap real quick what it means to reach an equilibrium. That means that we have a forward reaction rate. So if we look at the magnitude of the rates here, the rate of change will be changing for both the forward and the reverse rate because they're first order reactions typically. They're both going to be either decreasing or increasing until they reach the same spot. This is a lot like reaching terminal velocity. When you have a terminal velocity problem in physics, you have so let's just say physics analogy. Terminal velocity is reached once you have equating forces. So the force of gravity is the same, and then you have a force of drag that is increasing with increasing speed up until that equals the force of drag. But when you drop out of an airplane to go skydiving, you're not yet at terminal velocity. It takes a little while until you hit that equilibrium of the forces. So you could kind of think of it in that regard as well. That's kind of what happens, and in our chemical equilibrium equations, that happens pretty quick. So usually we get to the equal rates pretty quickly. Now, the equal rates does not necessarily mean we have equal amounts. So if we take a look at the graph here on the bottom, if we are looking at the amount of a chemical, so it could be, maybe this is H2O and this is OH minus or something in that equilibrium, we can see that once we reach equilibrium, there's a steady amount of it, but they're not necessarily the same, right? Even though we've reached equilibrium, the amounts can be different. Okay, so what does this look like if we're to graph a system across, let's say, pH? And we'll probably come back to this graph or this type of graph pretty often. So we have on the y-axis the fraction, that's a little alpha here. This is the fraction of, in this case, the carbonate system. And carbonate meaning really anything with CO3 in it. So CO3X with maybe something in front. Any of that has carbonate in it, right? That's the carbonate system. And so this is what we would call carbonic acid over here, the H2CO3. This is bicarbonate. And CO3 2 minus is carbonate. I mentioned last time that you're going to want to commit some of these things to memory, at least recognizing what is carbonate, that's the CO3. And essentially carbonate is dissolved CO2. So if we take CO2 gas and react it with water, then we're going to get, if we add that oxygen here, we essentially get H2CO3, right? So if we just add the water straight to that, that would be a reaction there. Technically, this is also going to be our Henry's law equilibrium, so we can have it have the gas dissolve, or let me just take a step. I misspoke a tiny bit. Henry's law does apply. What I'm going to say is aqueous, so dissolved CO2 gas. And this happens after CO2 gas goes into water through the Henry's law. So we'll write it that way. The point being, we get carbonic acid from dissolving CO2 in water. And it turns out that when you do that, then this carbonic acid, as it sounds, provides some acidity. Good question, thank you. This is the fraction of total carbonate in the system. So this is, let's see if I can write sideways. So this is the fraction of total CO3 species. So any type of CO3 rather, in the system. Right here, this means that all of the carbonate in the system is in this form. So if we track this line, then at some point right here, approximately half of the carbonate in the system is H2CO3. We can also take a look over here with the bicarbonate. Maybe 0.97, so 97% of all of the carbonate is in the bicarbonate form. So that's a great question, and what we're looking at is tracking that over pH. And essentially what's happening here is we added the carbonic acid, and this is going to be in equilibrium with HCO3. So it's going to dissociate to HCO3 minus the bicarbonate plus a proton, H plus. And that's this reaction right here. So these two are going back and forth, and it's being pushed one way or the other based on the amount of H plus in the system. So if we were to increase the H plus, that drives our pH lower. That means we're changing the ratios. So our pH then is acting like a way we can push the system one way or the other, and which is why we see this change plotted like this. You'll notice here, at this point, there's equal amounts. And if we were to take a look, this is something like 6.5, and so this is actually the value, the equilibrium value between those two. So then the KEQ for this system, I'm going to label this as 1, just to say this is reaction 1, and we'll have a reaction 2 over here. So this KEQ then is something like 6.5 based on looking at that. And we could probably look in the book and find that specifically, but I say 6.5, what I mean is 10 to the minus 6.5. Okay, because that's the point at which the we find that equilibrium. Now, if we push the pH at a different place, the equilibrium constant is still the same, but the amounts have changed. So we can obviously change the pH to have a pH over here, and then we're going to have more carbonic acid and less bicarbonate. And likewise, we could shift it other places. So the next reaction, this set of reactions, or 2, we'll just write it here. So in the second equilibrium reaction set, we have HCO3 minus in equilibrium with CO3 2 minus plus H plus. And you'll notice that the charge in these systems has to be equal. So on the left side here, we have one negative charge. On the right side, pardon me, we have a 2 minus and a 1 plus. So the net here is -1, the net here is -1. On the first reaction, we had a net of 0, and over here we have a -1 and a +1, so a net of 0. That you're going to find that in our reactions pretty much always. There's going to be a net amount, or a net charge equivalence across them. So I'm showing you this to kind of demonstrate how it can work, how our species are going to change based on that math. So for either one of these, actually, you know what we'll do, I'll describe it very specifically. So for the first case, the KEQ1 is going to be equal to the products of that reaction, so the HCO3 minus times H plus divided by the H2CO3. Okay, so whatever this KEQ really is, which is something like 10 to the minus 6.5, we can set that equal to this amount here, or this equation, and then solve for some portion of it. Maybe we know the ratio between the carbonate versus carbonic acid. Maybe we measured that somehow, and then we're asking ourselves, okay, well, given that, what's the pH? So we could solve the pH that way. Or maybe we have the pH, and then we want to know something about one of the other components, and then we can use some algebra and solve for that. For the second equation, the KEQ here, and I'll say KEQ2, that's going to be the same process where we have, in this case, our second reaction. We're going to have the CO3 2 minus times H plus, and that divided by our HCO3 minus. Okay, so that's the way we can write them out. This is kind of an example of what these equations look like when played out in terms of the fraction of this stuff. So because there's some total amount of CO2 dissolved into carbonate, and so there's some total amount of carbonate in the system, and we can adjust the pH positive or negative, and for the most part, we can, if we have a closed system, let's say, if we assume we have a closed system, we're not exchanging CO2 gas with the atmosphere, then there's going to be a constant total amount of carbonate in the system, regardless of where we push the pH. So that concept of, in a closed system, the total amount is very important. Something like phosphoric acid that goes through equilibrium but does not have any component that could escape to the atmosphere. There's no gas form of that, really. Something like that would be, you don't even have to assume it's a closed system. You're still going to deal with just the total phosphoric acid, or total phosphate in that case. So we'll give some example problems with this. We'll work through a few today. I'm going to make sure to do a lot of examples, and we'll do a lot tomorrow or next time as well. So we'll be revisiting this graph and this type of analysis. So just keep in mind that this system had two equilibrium reactions. Some might just have one. If we look at the chlorine system, free chlorine, it'll just have one. But this is kind of the concept here. Okay, for pH, specifically what we're looking at is the acid-base properties of water. So we know water, like I said before, can dissociate into H plus and OH minus, and it can go in reverse. I think I also mentioned that the K, the equilibrium constant for water, is equal to 10 to the minus 4. 10 to the minus 14. We also know that if we have a liquid or a solid like this, we can treat that type of stuff as just one. So this means that our KW, pardon me, my phone's ringing. Our KW is going to be equal to H plus times OH minus. And we're dividing this by 1 because that's That's our assumption that water here, we have so much of it that it really is unity. It doesn't really matter in comparison. We're not, and essentially what happens is, it turns out that the molarity of water, so the concentration of liquid water, if you do the calculation, is something like 54 moles per liter or something. It's in the 50s. And it turns out that if you take a small amount of that away to make H plus and OH minus, then you're really not having any change in the water here, any reasonable change. It's like 7 decimal places away, or at least 3, 4, 5 decimal places away where you might see any sort of a difference. So nowhere in our standard pH range does it really matter. And so we just can assume appropriately that goes to 1. So we'll just say that goes to 1. Okay, so that means Kw equals H plus times OH minus, and we can say that's equal to 10 to the minus 14. And if we take this at pH 7, at pH 7 is where we define the case where we are neutral acidity. That means if H plus is our acid, which that's a typical way to define it, and OH minus is our base, that means that at pH 7, at that neutral case, they're going to be equal. So we have OH minus equals H plus. When we have a situation like this, then one thing we could do is substitute. So we'll see a problem later, we'll take a look through it, and the problem's solution says, okay, let's call that S, and then for substitute. So we're going to substitute with a character S, and then we're going to say, okay, then Kw equals S squared. Okay, you don't have to use the S. You could have just left it as OH minus. You could have left it as H plus, because when they're equal, so at pH 7, let me just reiterate, at pH 7, we can do the substitution. We could say that that's Kw is equal to H plus squared. We could say that it's OH minus squared. However you want to write it, that the fact that we're at pH 7 and we know they're equal there, we get to write it that way. And then we can use that to solve, okay, what is our concentration there? And so we'll come back to that in just a moment. I want to introduce first what the P means, because if we can get a good understanding of what that P means, that simplifies a lot of other analysis here. So if we take pH, that's the same thing as saying the minus log of the molar concentration of H. So P then really means, so P refers to the minus log of the molar concentration of blank, whatever the P of the pH, the px, the POH, right? Whatever it is. Okay, so that means that if we take P of X, it's a minus log of the molar concentration of X. Remember these brackets, when you see the brackets, that is molar concentration. Always, always moles per liter. So the minus log of H plus then, when we're at pH 7, so when pH is equal to 7, that means we can solve for the H plus concentration at pH 7. So when we do that, just the very basic log rules here, minus log of the molar concentration of H. We're trying to solve for the molar concentration of H, so we can raise both sides. So we can raise 10 to the power of both sides to get rid of the log. That gives us H plus is equal to 10 to the minus 7, because we first divided, or took the negative to the other side, multiplied both sides by -1, let's say. So we moved to the negative, and then we have log of H plus equals -7. Then we take 10 to the power of both sides. That gets rid of the logarithm. and then we have 10 to the minus 7. We also know that at pH 7, where our acidity is neutral, and so we can say that's also equal to OH minus. Now, that means that H plus times OH minus equals 10 to the minus 4. That brings us back to this part where we say, okay, well, H plus squared equals 10 to the minus 14. And we can solve for, and we can see directly that H plus is then 10 to the minus 7, like we were just saying, right? There's a few ways to look at it. It all kind of interconnects here. And this is moles per liter. So another term for moles per liter is capital M. So I don't think I mentioned that last time, but in case you've forgotten, moles per liter, so let's say brackets, indicates moles per liter, also known as capital M. So if you see capital M as a unit, that's moles per liter. Okay? All right, so any questions on the P operator or this the water system here? There's some important points here. We'll have more opportunities to go through them, but definitely want to make sure that there's no issues at this point. Okay. So, where does it matter? Well, in just about every single aqueous system, we're going to have equilibrium chemistry. So whether that's understanding what kind of minerals are in our groundwater, whether that's how much CO2 is exchanging with the ocean or with rainwater, how much acidity is in our rainwater, so acid rain, the pace at which glacier melt is dissolving minerals from the mountain, all of this has at its core several equilibrium reactions at play at almost any time. If you get into this pretty deeply, geochemistry, or if this is something that is particularly interesting to you, geochemistry is essentially the study of equilibrium reactions within geological and water aquatic systems, and oftentimes in the context of identifying how minerals or how different elements are transferred through the environment. So you could take a look at the geochemistry of iron transport in estuary systems, or all sorts of things. It's really kind of the mineral chemistry aspect of environmental science and engineering. Another way it matters is we use equilibrium chemistry, solubility chemistry, all of these things in dealing with and understanding hardness. So water hardness, just briefly, is kind of essentially the mineral content of water. So how many minerals have dissolved into water. And if you look, in the US, there's quite a range. So I grew up and lived a lot of my life in or around Atlanta, somewhere around there. Then I lived for a couple years in Michigan, and now here we are somewhere in this corridor, right? So depending on where you go, it could even be just a few miles away, you might notice a tangible difference in the quality of the water, and not just the taste, but the way it interacts with soap in particular is fairly interesting. The amount of mineral content, so the hardness, if you have hard water, it's going to prevent soap bubbles from forming as well. So you need more soap to get suds. If you have really soft water, on the other hand, super soft water, you'll have plenty of suds, but then you never feel like you can get it off your skin. If you, let's say, showered and you're trying to wipe off the soap, it will feel like it never goes away. That's kind of an effect from the soft water side of it. Neither thing is particularly harmful. Hard water, you'll get some mineral scaling, so maybe some maintenance issues, but generally it's not like a health concern. It's just some mineral content. So there's some recommended range. So water treatment plants may adjust the hardness to keep it in a nice range, but otherwise it's not a big deal. So once you take EVEG 3110, which is the other class I'm teaching right now, you'll go into a bit of the water softening, and probably in the environmental chemistry as well, really dealing with how do you manipulate the mineral content. Well, a lot of it is using manipulation of solubility and of these reversible reactions, these equilibrium reactions. So by manipulating some things, you can cause things to precipitate. So calcium, magnesium kind of stuff is usually what we're thinking of when we're talking about hardness. Those are the major minerals that we're talking about. Of course, there's other stuff too. Okay, so speaking of solubility, that's the next topic I want to deal with. And here we have a table from our book, all sorts of different types of minerals and their equilibrium reactions. And what you'll see here is we're looking at solids for the most part here. So we have a solid aluminum hydroxide in equilibrium with Al3+ and OH-. And we have a pKs. They've just said that solubility here. And one thing before I continue, you'll notice here we have a P, so pKs, or you could have a pKa, pK, whatever subscript you want. The same P is the same operator. So it's another tool to say that let's say that if the pKa or pK whatever is equal to, in this case, 32.9, that means that the negative log of K equals 32.9. Okay, so that means that K equals 10 to the minus 32.9, which is a very small number. So a very small fraction of this, essentially what this is saying is a very small fraction of this, when put in water, remains as this solid. If I said that right. I think I said that backwards. A very small amount of this dissolves, right? Because in terms of water, we could say the pK for water is equal to 10 to the minus 14, and a very small amount of the H plus times OH minus divided by water, a very small amount of that is actually in the top two forms. It's significant, right? It's pH, it's acid-base chemistry, but the smaller this number up here, the smaller the K, and I'm sorry, I wrote that wrong. This would be the K water is 10 to the minus 14th, which means the pK water, and you guys should correct me here, that is 14. So the pK water is 14, which means the Kw by itself is 10 to the minus 14. Okay, hopefully that was not too confusing. But my point here is that when this is a large number on the pK or a very small number with the 10 to the minus whatever, that's telling us some ratio here, right? The smaller the number, the smaller the amount that dissolved. So this is very little dissolves. For having a high number there. So if you just take a look, let's glance at some other stuff. Aluminum phosphate, not a whole lot dissolves. Calcium carbonate, a fair bit of, looks like it's going to dissolve. So at least a reasonable amount compared to the other stuff. Ferric hydroxide, very little. Ferric phosphate, not a whole lot. Magnesium hydroxide, okay, we have some, a bit more than the water dissociation at least. This dolomite, not a lot. Kaolinite, a fair bit. And this is a bit more complex of a molecule here. It's a clay. Gypsum, a fair bit of solubility here. And we actually use gypsum in our drywall. Okay, so we'll take a look again at these. This is just a reference table. And one thing we will deal with next time as well is you can actually calculate these, the equilibrium and solubility products as, and by the way, when it's a solubility constant, they call them a product, solubility products, for whatever reason. So if we were to take a look at some of these, I guess the thermodynamics of the chemistry, we can actually solve for the pKa's, pKs's, whatever. We can solve for those, and we'll take a look at that, I think, next time. And then maybe we'll talk a little bit about thermodynamics and get into a bit of energy, a small section on energy from that. But for now, we're going to stick to, we have the pK value given, and so what do we do with that is kind of the next question. Okay, so here's our first example problem, example 2.6 in our book, or 2-6. If you add 30 grams of calcite, so CaCO3, to a 1 liter volumetric flask, and bring the final volume to 1.00 liters, what would be the concentration of calcium, Ca2+, in solution? Assume the calcium in solution is at equilibrium with CaCO3 solid, and the temperature of the solution is 25 degrees Celsius. So that's really just kind of referring to, the temperature there is referring to the way we could calculate, if we needed to, a change in the pK value. So it's giving us a pK value. 25 is a pretty standard temperature. That's about room temperature. And so if it gave us some funny number, then maybe we should think about that, but I haven't even taught you about that yet, so don't worry at all about that. For now, we just ignore the temperature, aside from just noting that it's a pretty standard temperature. Okay, so the pKs for calcite is 8.48. So the first thing you ought to do, and I'm showing the solution, the first part of it here, and we'll walk through what the book does here. But the first thing you ought to do is write out the relevant equation and make sure you can do that part. So it was saying, first of all, okay, what are we looking for? We're looking for Ca2+ concentration. Ca2+, and very likely we'll be looking for that in moles per liter. So let's assume we're looking for the molar concentration of Ca2+. So that's the question, and let's look at the relevant equation or equations that we have going on. So CaCO3 added to water, essentially, and we're going to form Ca2+. So if we take CaCO3 and we dissolve it in water, what we're likely going to get, we should have an equation here where it's just dissociating into the two. So Ca2+, and like we saw earlier, CO3 2-. Now, we'll double check that the charges are good. 2- and 2+ looks good. And that's just a polyatomic ion that we've seen before, and calcium we know can be an ion as well. So just like they showed, I'm just writing the same thing up. Another thing you ought to do is recognize that the pKa here, the pKs, was equal to 8.48. That means, like, as they're showing here, you could say that Ks equals 10 to the minus pKs. And so that means that the Ks is equal to 10 to the minus 8.48. Okay, so I'm going to give you just a couple minutes. I'm going to mute myself and step out for just a moment, but I'll be right back, and then we'll walk through how the book solves this. But give it a moment to think about how you're going to approach this type of a problem. Okay, and definitely add any questions you've got in the chat, and I'll be right back. Okay, so hopefully you had a moment to think about this. Let's see what the book says about it. So we have our Ks, and the first thing they're reminding us of is essentially our Ks is equal to, and they write with the squiggle brackets. I'm going to explain that briefly. We'll get into this next time. So they say it's going to be squiggle brackets for Ca and squiggle brackets for CO3 2 minus. They're leaving out the fact that you're also going to have the Ca CO3 solid here. The reason they're leaving that out is because they're assuming, since it's a solid, and I forgot the S there, since that's a solid, they can just basically get away with assuming it's 1, right? I mentioned that. Now the squiggle brackets, the squiggles are meaning that it's the activity of something, and if we have a relatively dilute solution, the activity is equal to the moles per liter. And it mentions this here. We will assume that the solution is dilute, allowing us to approximate the activities with molar concentrations. Most of the time we'll just do that, okay? We'll get into that, I'll explain it next time, but chances are I'm probably not going to make you do that on a test, maybe a homework problem. But like I said, we'll get to the math of that later. So just set that aside for now and recognize that, as they said, this is then equivalent to just Ks equals the Ca 2 plus times the CO3 2 minus molar concentrations. Okay, and then they're noting, okay, for every 1 mole that we dissolve here, we get 1 mole of each of these. And by that, we can say how many moles of this dissolved. That's going to give us the moles of calcium. And so what we're looking at here is, okay, sorry, let me rephrase that. So if you read what they say, they're saying is each one of these you dissolve, you get 1 of both of these. So 1 of each. And so that's where they're going to do the substitution thing, where they say, well, for every time you dissolve 1 of these, you're getting 1 and 1. So you're going to end up with the same amount. Again, we'll assume here this is a closed system. We're not going to lose any carbonate from degassing or anything like that. It gave no indication that that would be a concern, so we're just assuming that, you know, none of that matters. So then we can say Ca2 plus, the calcium, is equal to the carbonate, and we're going to set that equal to S. So that's what I was mentioning earlier in the water system, that you can arbitrarily say S. You could just leave it. You don't even have to have that, but you could use that. So then the next step would then be to solve, okay, well, what is the amount here? So it will be something like, well, we know 10 to the minus 8.48 is equal to S squared, or that's the same thing as equal to Ca2 plus squared, right? It's just a different way of articulating it there. So in that sense, we'll take a look, and presumably that's what they're doing. And yep, S squared equals 10 to the minus 8.48. And then when you solve, we have S is equal to Ca2 plus concentration, and then they do that solution, and it turns out the calcium is equal to 10 to the minus 4.24 moles per liter. Or you could write that out. I mean, you could leave it like that maybe, but I guess a nicer way to write it out would be to do that exponent and just write it out as in scientific notation instead. So then you have 5.75 times 10 to the minus 5th moles per liter. And it goes on to add a little extra context there. Okay, so does that kind of make sense? This one was pretty straightforward. In fact, most solubility things are going to be fairly straightforward. There are some complexities we can deal with, but we're going to keep it relatively simple. And I do plan to revisit the the Henry's law for gases in the equilibrium constant sort of a theme. Okay, so another question here, we have a magnesium hydroxide solution is prepared by adding 10.00 grams of magnesium hydroxide to a volumetric flask and bringing the final volume to 1.00 liters by adding water buffered at a pH of 7.0. The concentration, what is the concentration of magnesium in the solution? And again, we are assuming the temperature is 25 Celsius, and the ionic strength is negligible. So ionic strength here, and this is one of the book problems, by the way, this is going to be something that can be relevant to the activity. I mentioned we're going to deal with activity later. It's saying it's negligible, so that means we're going to treat it. We're just going to ignore it. We're going to ignore that activity thing and say that the brackets that we've been using are just fine. Now this one requires a lookup, so we need to look up the K solubility for magnesium hydroxide. You might also need to think to yourself, okay, well, what is magnesium hydroxide? And hopefully you remember magnesium is Mg, and if it's a magnesium ion, that's going to be 2+ typically. So you can look at the periodic table and hopefully be able to see that. Hydroxide is OH-. So if we're, another common one you probably should know just by name. And so if we have magnesium hydroxide, then what we're looking at is magnesium with a 2+ and hydroxide with an OH, which would have 1-. So we'll need 2 of those to balance. So magnesium hydroxide then should be MgOH2 solid. So that's what we're looking at. And before we launch into it, I might as well take a note. Looks like we have 4 significant digits here. Since we talked about this last time, we have 3 here and 2 here. So at the end of the day, we probably should report 2 significant figures for what that's worth. Okay, so let's take a look back to see if we have a value for our Ks from the lookup table. That's that table that we looked at earlier. We have magnesium hydroxide. So the pKs here was 11.25. So we'll say pKs 11.25. Okay, so the question's asking what is the concentration of magnesium in the solution. So let's see if you can find the answer to that. So take a minute to work on that. And I will rejoin you in a second, and we'll see what the book's answer was. Okay, so let's go ahead and start by writing out the equation here. We have magnesium hydroxide as a solid in equilibrium with magnesium and two hydroxides. So note here that those two hydroxides are going to dissolve and dissociate to two of those, and so that complicates the system a tiny bit more than we've done so far. So we have, when we write out our solubility, then it's equal to the Mg2 plus to the 1 power times OH minus that to the 2 power divided by 1. So when we first wrote out the equation, the general equation for these equilibrium reactions, we had, it was like A to the A power and so on. So that exponent there, it's important not to forget that. So we have then hydroxide squared, and we also were given some information about the hydroxide tangentially. So the pH was 7, so at pH 7, then H plus equals OH minus. That's the definition of our neutral case for acid base. It's equal to OH minus, and we know that from that being pH 7, that's equal to 10 to the minus 7 moles per liter. Okay, so you could also write as POH is 7. Same deal there, the pH or the POH is minus 7 at neutral. So that means we actually have pretty much everything we need here. We can say 10 to the minus 11.25. Again, remember the role of the P here is going to be very important repeatedly, so make sure you get that concept. So 10 to the minus 11.25 is equal to what we're looking for times something we know, 10 to the minus 7 squared. Okay, so then we can solve that. I'll do that in Excel real quick. So we're looking for right there, and we also know that the OH minus concentration is equal to 10 to the minus 7. Oops. And so then our magnesium concentration then, according to that equation, is going to be equal to this one, the Ks, 10 to the minus 11.25, which I solved there, by the way. That's, you can see just right there, that's 10 to the minus 11.25. So this is going to be equal to that divided by this guy squared. And we get a concentration there. Let me just double check that the square went to the right part of that. Okay. That looks wrong to me, so perhaps I did something incorrect. If you see something, oh, I'm sorry. Yeah. If you see that I did something wrong, let me know. Because I think that's wrong. I don't think we can have 562 molars of something. First of all, I completely forgot to factor in the fact that we added 10 grams of this stuff into 1 liter. So that would be a problem. And in fact, that probably is exactly the problem. I apologize. Okay, so if we had an infinite amount of this stuff, then maybe that would be true. Okay, so maybe I just solved if we had an infinite amount of magnesium hydroxide added to water. Okay, well that's not the case, so pardon me, that was silly. But at least it shows the extreme case. So that would correlate to, 562 moles per liter of Mg2 plus. Clearly the wrong approach. So I'm going to write here, need to factor in the 10 grams in 1 liter. So just make it clear that, and I apologize for the confusion that this may cause, this was not really the right way to do it. That would be if we had an infinite source, if it truly was like completely solid. So maybe that's something okay to do, to check, to make sure that we're not providing an answer that is too, maybe we could have a case where we expressed an answer that was actually under the solubility limit. This would be the solubility limit. So instead, what we can do is say 10 grams in 1 liter. So that's 10 grams per liter. So let's see the molar concentration of that for magnesium hydroxide. So we'll need the molecular weight for magnesium hydroxide, and that I need to look up real quick. Could do this, of course, on a periodic table, or Wikipedia tends to have these handy. And so if you take a look at magnesium hydroxide, here we are, MgOH2, we're at 58.3 grams per mole. So we will write that in here. 58.3 grams per mole. And so if we take that 10 grams per liter, we can divide this by 58.3 grams per mole. That should give us moles per liter. So let's go back to our Excel. So the amount we added in there was 10 divided by 58.3. That should be 0.17 moles per liter of MgOH2. Okay, so with that, write that in. .17 moles per liter. If we're looking for the concentration of magnesium in the solution, well, one thing we can see here is we get, for every 1 mole of this we dissolve, we have 1 mole of Mg2+. And so really that's going to be our answer. And the other stuff that I did was really only relevant to just double check that we were below, this has to be below the absolute limit. So what I'll say here is this is the solubility limit. So the fact that we had this this Ks provided, or that we went back and looked up Ks. They didn't even provide it, so silly me for just jumping to conclusions here. We probably ought to have checked to make sure we were under that solubility limit, to make sure it was reasonable. So let's just double check that this is the answer they provide. There we go. Awesome. And by the way, this was hidden from me. I didn't bother paying attention to it. So really that was a real-time process of making the mistake of doing it wrong and then correcting with you. So hopefully that makes some sense. So our answer, so let's say our answer should be less than the limit, right? And we can very clearly see that 0.17 is much lower than 560. By the way, they did use 2 significant figures here. Technically, in my response here, I should have written that as 560 to keep 2 significant figures. So, okay, there we go. That's that problem. We have another problem here. I think this is simple enough. We'll go ahead and launch into it. Take 5 minutes to work on this, and then I will review it with you, the process for the end of, and that'll be the end of class. So here we have a solution has an H plus concentration of 10 to the minus fifth moles per liter. Part A asks, what is the pH of the solution? And part B asks, what is the pOH of solution? And again, it's saying, assume that the temperature of the solution is pretty much room temperature, so we don't have to think of anything weird or different. We'll do some more problems next time as well. Definitely want to make sure that these concepts, there are a fair number of concepts that we're dealing with, and I want to make sure you have ample time to deal with them. Okay, so question for the last problem, wouldn't you have to use the 0.17 moles per liter as the denominator for the Ks equation? So I'm going to answer that. Feel free to mute me for a moment if you're working on this problem and want to focus on it. But great question, and I'm going to try to answer that off to the side here. So what you're asking essentially is, for the solubility limit problem earlier, we were looking at Mg2 plus, which is what we're solving for, times OH minus. We had that squared, and you're wondering, why did we not say that the molar concentration here for the MgOH2 solid, why didn't we put the 0.17 moles per liter there and then solve? It's a good question, and so thank you. Essentially, once this is dissolved, it's no longer the solid. And so you could, let's see. I don't think that that will work out. We could try it real quick and say, you know, we're trying to solve for magnesium 2 plus. If we solved for this, I mean, it's a little redundant because we already said some amount of it dissolved. So as long as that amount that dissolved, let's see. I guess the answer really is it's not possible. It's not possible because it all dissolved. So you no longer have a solid here. So this is not the concentration. So on the denominator here, this is not, when we put a solid here, that assumes that there is still some solid in solution to be in equilibrium with. Since we found essentially that it's all going to dissolve, then we don't put it there. because we already know that the MgOH2 basically all went to Mg2 plus and OH minus. So the fact that we already know that molar ratio there, yeah, I think it's just kind of redundant, because so if we have a solid here and then we no longer have any solid, it's just all going to be Mg2 plus and the OH minus. I'll take a look at that and try to give a better answer next time, to articulate that better. It is a good question, but I just don't think it makes sense, because this is presuming there's still a solid there, is all it is. And so we didn't end up needing the solubility constant at all for the final calculation. We could find this just so long as we knew that our answer was below the solubility limit. I think that's the case here. We'll work some more problems with solubility next time as well. Okay, did that help at all? I will try to be more clear on that next time. All right, I'm going to go ahead and answer the current question here. This was from the last problem. Happy to come back to that, so let me know if you're still confused, which I feel like might be the case since I didn't explain that very well. But we'll go ahead with this problem, and then I'll come back to questions either way. Okay, so what is the pH? Well, we talked about this. The P of H plus is equal to the negative log of H plus. And so when we see a 10 to the minus fifth moles per liter for H, that really is just going to mean that our pH is 5. So that should be fairly straightforward, just kind of looking at it. Now the pOH is a little interesting. You might deduce here, this is 2 logs away from 7, and so the pOH should probably be 2 logs away from 7 in the other direction. So I think this should be correct to say that that's 9, but let's double check that mathematically. So we'll add a question mark there. So to do it mathematically, what we want to do is say our K water is equal to 10 to the minus 14. By the way, you should probably commit this to memory. The equilibrium constant for water is 10 to the minus 14. It's a kind of a universal thing. That's how the pH system, it's the basic principle of the pH system. That's why we range our pH. If you're to look at a pH meter or a pH strip, basically 0 to 14. There are some ways maybe you can adjust the boundaries a little bit with some extreme cases, but generally this is our range from 0 to 14 for the pH. So pOH then, what we need to find is the OH concentration, OH minus. And so we know that 10 to the minus 14 is going to be equal to OH minus times H plus divided by the 1 from the water. And so here we were given the H concentration, 10 to the minus fifth. So really all we need to do is solve for the OH. So the OH minus is equal to 10 to the minus 14 divided by 10 to the minus 5. And if you remember from the log rules, you can actually, when you divide like this, you can essentially take 5 away from the 14, and this is equal to 10 to the minus 9th. So like I suspected earlier, this means that P of OH is equal to 9. So you can't always just say, oh, it's this number of logs away. It is correlated in that manner, but maybe it's something more complicated. So it would be helpful to understand that you can do the process this way. You could also take this and solve it in Excel and prove to yourself that relationship does hold true if you forgot the exponent rules there. But assuming we did all that right, yep. So pH 5 and pH 9, or POH 9. Okay, any other questions? I think we'll do this last problem next time. Probably a few more problems. Any questions for now? Thank you guys, by the way, for participating, asking questions. I know it's kind of awkward. I guess last year we had plenty of this, but hopefully you found this useful and not too different than in person. I certainly like to be able to not worry about a commute, so no qualms here. Okay, so that's all I've got for you. We'll see you guys in person on Tuesday next week, and I'll try to get a homework posted for you pretty soon, maybe by Tuesday. All right, so with that, have a good weekend and enjoy the fall break as much as you can.